The speed of light is often described as unimaginably fast. At 299,792 kilometers per second, it circles Earth more than 7 times in a single second, reaches the Moon in 1.3 seconds, and arrives from the Sun in just over 8 minutes. On human scales, it appears effectively instantaneous. That intuition is profoundly misleading. The moment distances become interstellar, the fastest speed allowed by physics begins to look remarkably slow. Light takes more than 4 years to reach the nearest star beyond the Sun. Crossing the Milky Way at light speed would require roughly 100,000 years. No spacecraft with mass can reach this velocity, and every realistic propulsion system is dramatically slower. This transforms the speed of light from a triumph into a limitation. It is not merely the fastest speed in the universe, it is the maximum speed, a hard boundary written into space-time itself. The unsettling possibility is that this limit does more than restrict travel. It may permanently isolate intelligent civilizations from one another across the galaxy. The speed that only feels fast. Light, leaving a flashlight in your hand, reaches the wall across the room in roughly 10 billionths of a second. A radio signal from a spacecraft in Earth orbit arrives at a ground station before any human sense could perceive the transmission had begun. The delay is real but irrelevant to communication at these distances. Flip a light switch and the room illuminates. The physics is instantaneous by any human standard of measurement. This experience is the foundation of the intuition that the speed of light is approximately fast enough for any conceivable purpose. It is an intuition shaped by evolution on a planet whose diameter is about 12,700 kilometers, whose circumference is roughly 40,000 kilometers. On these scales, 299,792 kilometers per second is effectively infinite. You cannot perceive the delay. You cannot measure it without precision instruments. The mental image formed in childhood of light as essentially instantaneous is accurate for every experience of life on Earth. The moment you leave Earth's immediate neighborhood, this intuition begins to fail. The Moon, at an average distance of 384,400 kilometers, introduces a 1.3-second delay in radio communication. During the Apollo missions, Mission Control in Houston experienced this delay in conversations with astronauts on the lunar surface. The delay was noticeable, but manageable. A conversation with a 1.3-second round-trip delay requires patience, but not fundamentally different communication strategies. The intuition bends slightly, but does not break. Mars breaks it. At its closest approach to Earth, roughly 54.6 million kilometers, the communication delay between Earth and Mars is approximately 3 minutes each way. At its farthest, when the two planets are on opposite sides of the Sun, the separation extends to approximately 401 million kilometers, and the one-way delay climbs to approximately 22 minutes. NASA engineers operating the Perseverance rover on Mars's surface experience this delay acutely. The rover cannot be driven in real time. It receives command sequences developed on Earth, executes them autonomously, and reports results after the communication delay. Direct conversational exchange is impossible. A question asked takes 22 minutes to arrive. An answer takes 22 minutes to return. A back and forth interaction that would take 3 minutes on Earth requires nearly an hour and a half when one party is on Mars at maximum separation. And Mars is in our own solar system. Mars is close. Light reaches Mars in minutes from the Sun, in tens of minutes from Earth. On the scale of the galaxy, Mars and Earth are essentially the same point in space. The entire solar system, from the Sun's outer corona to the outer edge of the Oort cloud at roughly 100,000 astronomical units, measures approximately 1.5 light-years across at its most generous definition. The nearest star, Proxima Centauri, is 4.24 light-years away. The gap between the edge of our solar system and the nearest stellar neighbour spans approximately 2.7 light-years of essentially empty space. Light crosses that gap in 2.7 years. A radio signal sent toward Proxima Centauri today will not arrive for more than 4 years. A reply, if anyone were listening and inclined to respond, would not reach Earth until 2034 at the earliest. This is the nearest case. It is the best possible scenario for interstellar communication delay, and it involves waiting 8.5 years for a question and answer exchange with the closest stellar neighbour. Scale outward to the distances that actually separate most stars from one another, and scale further to the distances that separate potentially habitable worlds from Earth. And the speed of light stops being fast and becomes instead the primary obstacle to any meaningful contact between civilizations. The distance to Proxima Centauri in familiar units is approximately 40.2 trillion kilometers, or 25 trillion miles. The number is large enough that it resists intuitive grasp. At the cruising speed of a commercial aircraft, approximately 900 kilometers per hour, the journey to Proxima Centauri would take approximately 5.1 billion years. That is slightly longer than the current age of the Earth. At the speed of the Voyager 1 spacecraft, the fastest human-made object currently moving through interstellar space at approximately 17 kilometers per second, the journey would require roughly 74,900 years. The entire span of human history, from the emergence of modern behavioral complexity through the present, fits easily into less than 15% of that travel time. Light covers the same distance in 4.24 years. The contrast between these numbers is the foundation of the problem. Light is nearly 25,000 times faster than Voyager 1. It is approximately 600,000 times faster than a commercial airliner, and it still needs more than 4 years to cross the distance to the nearest star. Any physical object, any spacecraft, any probe, any vessel carrying information in material form will need more time than light, always more, often vastly more. What light years actually measure. The light year is defined as the distance light travels in 1 Julian year of exactly 365.25 days, at its vacuum speed of 299,792.458 kilometers per second. The result is approximately 9.461 trillion kilometers, or 5.879 trillion miles. This is a unit of distance, not of time, although its name contains the word year. A common confusion about light years is that they describe how long something takes to travel. They do not. They describe how far light travels in a year, which is then used as a convenient unit to express cosmic distances. The unit is necessary because the alternatives are impractical. Expressing the distance to Proxima Centauri in kilometers produces the number 40,208,000,000,000, a 13-digit figure that cannot be held meaningfully in mind. Expressing it in light years produces 4.24, a number that fits in working memory. The trade-off is that the unit itself, the light year, is so physically enormous that the number it produces also cannot be held intuitively even when it appears small. The compactness of the notation conceals the immensity of the quantity. 1 light year is approximately 63,241 astronomical units, where 1 astronomical unit is the mean distance from the Earth to the Sun. The distance from the Earth to the Sun is 150 million kilometers. Multiply that by 63,241 and you get 1 light year. Multiply that by 4.24 and you get the distance to Proxima Centauri. The Earth-Sun distance, which already feels vast on human scales, becomes the small unit in a calculation that produces a number that is still only the nearest star. The light year also encodes a temporal relationship that becomes significant when thinking about interstellar communication and travel. When we observe Proxima Centauri, we are seeing it as it existed 4.24 years ago. The light arriving at Earth tonight from that star departed before it could reflect any event occurring on or near Proxima Centauri in the past 4 years. If a planet around Proxima Centauri experienced a catastrophic event last year, we would not detect the light associated with that event for another 3 years. The star as we observe it is always a historical record, never the present moment. This temporal displacement grows with distance. The stars of the Orion Nebula, approximately 1,344 light-years away, appear to us as they existed in roughly the year 680 CE. The Andromeda Galaxy, 2.537 million light-years away, appears as it existed before the genus Homo had fully evolved. The most distant objects observed by the James Webb Space Telescope, at redshifts corresponding to distances of over 13 billion light-years, show us the universe as it existed when the Earth did not exist, when the Sun did not exist, when the Milky Way was still in its early formation. The observable universe is a temporal archive, not a contemporaneous snapshot. For interstellar communication, this temporal displacement means that any signal sent across interstellar distances is necessarily a message from the past. A civilization receiving a signal from Earth tonight at a distance of 100 light-years is receiving information about Earth as it existed a century ago. The civilization currently on Earth, in whatever form it takes 100 years from now, will be the one receiving any reply. The individuals who sent the original signal will be dead. Entire cultural and political configurations will have changed. The contact, if it happens, connects different temporal versions of each civilization rather than their contemporaneous selves. For physical travel, the temporal displacement means something even more consequential. A spacecraft travelling at 10% of the speed of light toward a star 100 light-years away will arrive 1,000 years after its departure. The civilization on Earth 1,000 years from now will receive any communication sent back from that spacecraft. The civilization that launched the spacecraft will be entirely gone, replaced by societies whose connection to the launching civilization may be as tenuous as our connection today to the civilizations of the year 1025 CE. The deeper implication is that a light year is not merely a unit of distance. It is a unit of historical separation. Every increase in distance corresponds to an increase in the age of the information available about the object being observed. Looking farther into space is therefore identical to looking farther into the past. Astronomy is unique among the sciences in that its primary data source consists almost entirely of delayed information. This delay is negligible at human scales. Sunlight reaching Earth is 8 minutes old. The light reflected from the Moon is approximately 1.3 seconds old. These delays are small enough that they do not meaningfully alter our perception of events. At interstellar distances, however, the delay becomes the dominant feature of the relationship. The nearest stars are observed years in the past. Large regions of the galaxy are observed centuries or millennia in the past. Other galaxies are observed millions or billions of years before the present moment. The result is that the universe visible from Earth does not exist as a single synchronized reality. Different objects are observed at different moments in their histories depending on their distance. If two civilizations exist on opposite sides of the Milky Way, separated by 100,000 light-years, each observes the other as it existed 100,000 years ago. Neither civilization can ever directly observe the other's present state. The finite speed of light prevents any shared experience of simultaneity across such distances. This has profound consequences for the search for extraterrestrial intelligence. Even if technological civilizations are common, communication between them may be constrained not only by distance, but by time. A civilization could emerge, develop advanced technology, and disappear entirely before its first detectable signals reach another civilization hundreds or thousands of light-years away. By the time a reply arrives, both societies may have changed beyond recognition or cease to exist altogether. The light year therefore measures more than space. It measures the minimum separation between cause and effect across the cosmos. Every observation, every message, every attempted act of communication is constrained by the fact that information cannot travel faster than light. The universe we see is a record of what has already happened, and the farther we look, the older that record becomes. In this sense, the night sky is not a view of distant places. It is a layered archive of different eras of cosmic history, with every point of light representing a different chapter in time. The stars above Earth tonight do not belong to a single moment. They belong to thousands, millions, and in some cases billions of different moments, all arriving together because the speed of light is finite. The nearest candidates and their actual distances. The distribution of potentially habitable worlds around nearby stars is not uniform, and the distances involved, even for the most optimistic nearby candidates, expose the practical limitations of interstellar communication and travel at any speed below that of light. Proxima Centauri b, announced in 2016 from observations by the European Southern Observatory, orbits Proxima Centauri at a distance of approximately 0.049 astronomical units, with an orbital period of 11.2 Earth days. The planet's mass is at least 1.07 times that of Earth. It receives stellar flux approximately 65% that of Earth from the Sun, placing it within the traditional habitable zone of its host star. These parameters initially suggested a potentially habitable world, and the announcement generated enormous scientific and public interest. The complications are significant. Proxima Centauri is a red dwarf star with a mass approximately 12.2% of the Sun's mass and a luminosity approximately 0.17% of the Sun's. To receive habitable zone stellar flux, Proxima Centauri b orbits so close to its star that tidal locking is essentially certain. One hemisphere permanently faces the star in perpetual day, while the opposite hemisphere faces away in perpetual night. The stellar environment is also much more violent than the Sun's. Red dwarfs are magnetically active, producing frequent and intense ultraviolet and X-ray flares. Proxima Centauri b, orbiting at such close range, receives stellar flare radiation roughly 100 times more intense than Earth receives from equivalent solar flares. Whether any atmosphere could survive this bombardment, and whether any life could persist in such an environment, remains deeply uncertain. As of 2026, no direct detection of an atmosphere on Proxima Centauri b has been achieved. Despite these complications, Proxima Centauri b represents the closest known exoplanet candidate. It is at 4.24 light-years. A radio signal sent today arrives in 2030. Any reply returns in 2034. The round-trip communication time for a single exchange is over 8 years. The TRAPPIST-1 system, located approximately 39.5 light-years from Earth, gained extraordinary attention in 2017 when the announcement of 7 roughly Earth-sized planets in orbit around an ultra-cool red dwarf star was made based on data from the Spitzer Space Telescope and ground-based observatories. 3 of the 7 planets, designated TRAPPIST-1e, TRAPPIST-1f and TRAPPIST-1g, fall within or near the system's habitable zone. The system has been a major target for follow-up characterization by the James Webb Space Telescope, which has begun examining the thermal emission and reflected light from the planets to search for atmospheric signatures. Results from JWST observations of TRAPPIST-1b and 1c, the 2 innermost planets published in 2023, found no evidence of thick carbon dioxide atmospheres on either. The data for the habitable zone planets remain more limited, and characterization of potentially habitable worlds in the TRAPPIST-1 system will continue as a major scientific priority through the late 2020s. TRAPPIST-1 is 39.5 light-years away. A signal sent today arrives in 2065. A reply returns in 2105. A single exchange, one question and one answer, requires 80 years. A person born today who sent a signal to TRAPPIST-1 at birth would receive any reply at age 80. A meaningful scientific dialogue, the kind of back and forth exchange that characterises actual communication, would span lifetimes. Physical travel to TRAPPIST-1 at 10% of the speed of light, far beyond any current propulsion capability, would require 395 years. Tau Ceti, a G-type star broadly similar to the Sun, located approximately 11.9 light-years from Earth, has been detected with a multi-planet system. Tau Ceti E and Tau Ceti F have been proposed as potentially habitable zone candidates, though confirmation of their properties remains uncertain, and the system shows evidence of a substantial debris disk that may indicate a higher impact rate than Earth experiences. The distance of 11.9 light-years means a one-way signal delay of nearly 12 years and a round-trip communication time of nearly 24 years. The pattern across all nearby candidates is the same. Every potentially interesting target involves communication delays measured in years to decades. Physical travel at any realistic speed involves timescales measured in decades to centuries for the nearest, and millennia for even modestly more distant systems. The galaxy's nearest stellar neighbourhood, within perhaps 20 light-years, contains perhaps a dozen star systems, with combined perhaps 24 individual stars. The fraction of these stars hosting planets with properties suggesting potential habitability is uncertain, but probably small. Yet even this densest, closest sample requires communication and travel timescales that strain or break conventional human institutions and planning horizons. The rocket equation and why chemistry cannot help. The physical barrier to interstellar travel is most precisely captured in a single mathematical relationship published by Konstantin Tsiolkovsky in 1903. The Tsiolkovsky rocket equation expresses the relationship between a rocket's final velocity, its exhaust velocity, and its mass ratio, defined as the initial mass divided by the final mass. The equation is delta V equals exhaust velocity times the natural logarithm of the mass ratio. The consequences of this equation for interstellar travel are devastating. Because the natural logarithm function grows very slowly, the mass ratio required to achieve a given velocity, multiple of the exhaust velocity, grows exponentially. To achieve a final velocity equal to the exhaust velocity, you need a mass ratio of approximately 2.72, meaning roughly 63% of your initial mass must be propellant. To achieve a final velocity twice the exhaust velocity, the mass ratio grows to approximately 7.4, 3 times approximately 20, 4 times approximately 55, 5 times approximately 148, 10 times approximately 22,026. Each additional multiple of exhaust velocity you want to achieve requires exponentially more propellant. Chemical rockets, the technology that has lifted every satellite, every crewed spacecraft, every planetary probe ever launched by humanity, achieve exhaust velocities of approximately 4 to 4.5 kilometers per second for the most efficient combinations of liquid hydrogen and liquid oxygen. The absolute theoretical maximum for any chemical propellant is approximately 5.5 kilometers per second, constrained by the energy available from chemical bond formation and breaking. The escape velocity from Earth's surface is approximately 11.2 kilometers per second, already more than twice the exhaust velocity of the best chemical propellants. The rocket equation tells us that escaping Earth's gravity from the surface requires a mass ratio of approximately 14. For every kilogram of payload in orbit, the launch vehicle must carry roughly 13 kilograms of propellant at liftoff. This is why orbital launch vehicles are so large and so expensive, and why so little payload reaches orbit relative to the total mass of the rocket. Interstellar speeds are on an entirely different scale. 1% of the speed of light is approximately 3,000 kilometers per second. that is nearly 700 times Earth's escape velocity. To achieve 3,000 kilometers per second, using chemical propellant with an exhaust velocity of 4.5 kilometers per second, the rocket equation requires a mass ratio of E raised to the power of 667, which is a number so astronomically large it has no physical meaning. The observable universe does not contain enough matter to build such a rocket. This is not a failure of engineering that better design can overcome. It is a mathematical consequence of the exponential relationship between velocity and mass ratio, combined with the fixed ceiling on chemical exhaust velocity imposed by the energy density of chemical bonds. No chemical rocket can achieve interstellar speeds. The physics forbids it categorically, not incrementally. Ion propulsion, used on missions including Dawn and Hayabusa, achieves exhaust velocities of approximately 30 to 80 kilometers per second by accelerating ions electrically rather than through combustion. This is a meaningful improvement over chemical rockets, producing higher efficiency for low-thrust applications in the inner solar system. But 80 kilometers per second is still only 0.027% of the speed of light. At this speed, the journey to Proxima Centauri would take approximately 16,000 years. Nuclear thermal propulsion, which uses a fission reactor to heat a propellant to high temperature before expelling it, can achieve exhaust velocities of approximately 8 to 9 kilometers per second, roughly double the best chemical performance. This is a significant improvement for solar system missions, but makes essentially no difference for interstellar travel. At 9 kilometers per second exhaust velocity, the mass ratio required to reach 1% of light speed still far exceeds any conceivable vehicle design. The only known propulsion concepts that could in principle approach interstellar relevant speeds are nuclear pulse propulsion, fusion propulsion, and laser-driven light sails. Nuclear pulse propulsion, studied under Project Orion in the late 1950s and early 1960s, uses the sequential detonation of nuclear devices behind a spacecraft to drive it forward. Exhaust velocities of tens of thousands of kilometers per second were theoretically achievable, and a Project Orion design scaled to interstellar mission requirements would reach perhaps 3 to 5% of the speed of light. But Project Orion was never built. The political barriers to deploying nuclear detonations in space are substantial, and even at 5% of light speed, the journey to Proxima Centauri takes 85 years. Fusion propulsion, using the controlled fusion of deuterium and helium-3 or other fuel combinations, could in principle achieve exhaust velocities of a few percent of the speed of light, sufficient to accelerate a spacecraft to perhaps 10 to 12% of light speed for a large enough fuel fraction. The British Interplanetary Society's Project Daedalus study in the 1970s designed a fusion-powered flyby probe to Barnard's star, reaching approximately 12% of light speed. The design required roughly 50,000 metric tons of fuel, primarily helium-3, a rare isotope on Earth available in useful quantities primarily from the lunar surface or the atmospheres of outer planets. No fusion engine has ever been built. Sustained controlled fusion for power generation remains unachieved commercially as of 2026. Fusion propulsion for spacecraft is an entirely theoretical concept with no demonstrated components. Laser-driven light sails, the approach pursued by the Breakthrough Starshot initiative announced in 2016, propose accelerating a gram-scale spacecraft to 20% of the speed of light using a ground-based laser array of approximately 100 gigawatts directed at a reflective sail. The engineering challenges identified in subsequent analysis were severe. Maintaining beam coherence and focus over the millions of kilometers of acceleration distance required, designing a sail that reflects rather than absorbs nearly all incident laser power, when absorbing even a small fraction of 100 gigawatts would vaporize any known material, protecting the chip-scale spacecraft from interstellar dust impacts at relativistic speed over a journey lasting decades, and enabling any meaningful communication back to Earth from a chip-scale transmitter across 4 light-years. By 2025, Scientific American reported that Breakthrough Starshot had spent only approximately $4.5 million of its pledged $100 million funding and had been placed on indefinite hold, as the engineering obstacles had proven more severe than initial assessments suggested. The energy wall that scales with velocity. Beyond the rocket equation's mass ratio problem lies a more fundamental barrier: the raw energy cost of accelerating any mass to interstellar relevant speeds. This cost is set not by propulsion engineering, but by physics, specifically by the relationship between kinetic energy and velocity described by relativistic mechanics. At speeds well below the speed of light, the kinetic energy of an object is well approximated by the classical formula: 1/2 times mass times velocity squared. As velocity approaches the speed of light, the correct relativistic formula must be used, which gives kinetic energy as rest mass energy times the quantity 1 over the square root of 1 minus velocity squared over the speed of light squared minus 1. The practical consequence is that kinetic energy grows without bound as velocity approaches light speed, requiring infinite energy to actually reach it. At 90% of light speed, the required energy is already 2.29 times the rest mass energy in equivalent. At 99%, it is 6.09 times. At 99.9%, it is 21.4 times. The curve steepens asymptotically, making the final few percent of light speed progressively more energy expensive than all the preceding acceleration combined. At 10% of the speed of light, approximately 30,000 kilometers per second, a spacecraft massing 1,000 kilograms, roughly the mass of an empty small car, carries kinetic energy of approximately 4.5 times 10 to the power of 17 joules. This is equivalent to approximately 108 megatons of TNT, or roughly 2 times the total nuclear explosive yield in all currently deployed nuclear weapons globally. Providing that energy at perfect efficiency, converting it entirely into spacecraft kinetic energy with no losses, requires consuming approximately 5 kilograms of matter completely via matter-antimatter annihilation. Providing it through nuclear fission, which converts approximately 0.1% of fuel mass to energy, would require approximately 5,000 kilograms of fissile material. Through the best conceivable fusion reactions, converting approximately 0.7% of fuel mass to energy, approximately 715 kilograms of fusion fuel, and this is for a 1,000 kilogram probe. A spacecraft capable of supporting a human crew, with the life support systems, radiation shielding, food and water, medical equipment, propulsion and structural mass required for a multi-decade journey, would conservatively mass hundreds of thousands to millions of kilograms. Scale the energy requirements accordingly. A 100,000 kilogram crewed spacecraft at 10% of light speed requires energy equivalent to roughly 10 billion tons of TNT, or approximately 20 million times the Hiroshima bomb's yield. A 1 million kilogram spacecraft, still modest by the standards of what crewed interstellar travel would require, multiplies that by 10 again. These numbers do not represent barriers that better technology can push aside. They are the actual physical content of the kinetic energy the spacecraft must carry, set by conservation of energy and the properties of mass and velocity. No engineering innovation can reduce the kinetic energy of a given mass moving at a given speed. That energy is what it is, determined by nature. The question is only where it comes from, and at these scales, the answer exposes the limits of every conceivable energy source. The total annual energy consumption of human civilization as of 2024 is approximately 6 times 10 to the 20 joules. A crewed interstellar spacecraft at 10% of light speed, massing 1 million kilograms, requires approximately 4.5 times 10 to the 22 joules for the acceleration phase alone. That is roughly 75 years of total human energy production, dedicated entirely to accelerating a single spacecraft to a speed that still requires 50 years to reach the nearest star. And it says nothing about the deceleration required to stop at the destination. The energy requirement creates a problem that extends beyond propulsion and into the scale of civilization itself. Interstellar travel is often imagined as an engineering challenge, a matter of building a sufficiently advanced spacecraft. But the energy calculations reveal something different. The spacecraft is only the final product. The real requirement is the industrial system capable of producing and directing the energy needed to move it. Throughout history, transportation has become possible whenever societies developed enough energy to support it. Ocean crossings required ships and sails, but also forests, ports, and economies capable of sustaining them. Railways required steel industries and vast fuel supplies. Spaceflight required entire national economies devoted to the development of rockets, launch facilities, and manufacturing networks. Interstellar travel extends this pattern to an extreme conclusion. The vehicle itself becomes almost secondary to the infrastructure required to launch it. This is why many serious studies of interstellar missions eventually begin discussing projects that operate on the scale of planets and star systems rather than individual spacecraft. The energy needed to cross the gulf between stars is so large that it becomes difficult to imagine generating it through any infrastructure confined to a single world. A civilization attempting such a mission would likely need access to resources distributed across much of its planetary system, harvesting energy continuously and directing a significant fraction of that output toward a single objective. The deeper implication is that the barrier between the stars may not primarily be a technological one. It may be an economic and energetic one. The laws of physics do not forbid travel to other stars. They simply demand payment in energy, and the price is extraordinarily high. Every proposed propulsion system, from fusion drives to antimatter engines to laser-push sails, ultimately confronts the same reality. Different technologies change how the energy is delivered, stored, or converted into motion, but none eliminate the underlying requirement. The distances between stars are often described as vast, and they are. But distance alone is not what makes interstellar travel difficult. The true obstacle is that crossing those distances requires concentrating an extraordinary amount of energy into a single object and maintaining that investment over timescales that exceed most human institutions. The challenge is not merely reaching another star. It is assembling the resources of a civilization on a scale that makes reaching another star possible in the first place. The deceleration problem that doubles everything. The energy cost described previously applies only to acceleration. Any mission that intends to do anything useful at its destination, orbit a planet, deploy surface landers, conduct sustained observations, or actually have any hope of extracting scientific value from the immense investment in the journey must also decelerate upon arrival. And deceleration costs exactly as much energy as acceleration. For a rocket carrying its own propellant, the deceleration requirement is far worse than simply doubling the energy budget. The fuel needed for deceleration must itself be accelerated during the outbound journey. Under the Tsiolkovsky equation, the propellant mass for deceleration adds to the initial mass of the spacecraft at departure, which then requires additional propellant to accelerate that propellant, which further increases the initial mass, which requires still more propellant in a compounding cascade. The total mass ratio for a mission that accelerates to cruise speed and then decelerates to rest at the destination is the square of the mass ratio for acceleration alone, not simply double it. If acceleration to 10% of light speed requires a mass ratio of 10 to 1, the full mission requiring deceleration requires a mass ratio of 100 to 1. If acceleration requires a mass ratio of 20, the full mission requires 400. The exponential nature of the rocket equation means that adding deceleration capability does not merely double the difficulty. It squares it, transforming already extraordinary propellant requirements into requirements that are orders of magnitude more severe. External deceleration mechanisms have been proposed to avoid carrying deceleration propellant. A magsail, which deploys a large superconducting loop to interact with the plasma of the stellar wind of the destination star, could in principle provide braking force without expending onboard propellant. The effectiveness of a mag sail depends on the density of the solar wind at the approach distance and the size of the magnetic sail. Calculations suggest that a spacecraft approaching at 10% of light speed would need to begin mag sail deceleration at distances of many astronomical units from the destination star, and the deceleration would require years at low thrust. The sail would need to be many kilometers in diameter and maintain superconducting operation throughout the journey and approach. A photon sail could theoretically use the radiation pressure from the destination star to brake as the spacecraft approaches, reflecting starlight to generate a retarding force. This is elegant in principle. The energy source is already at the destination, eliminating the need to carry deceleration propellant. But the force available from stellar radiation pressure scales with the star's luminosity and the sail's reflectivity and area, and the deceleration force must be sustained for long enough at sufficient magnitude to reduce the spacecraft's velocity from 10% of light speed to orbital or landing speed. For a spacecraft with any significant mass, the sail area required and the precision of alignment needed to maintain effective deceleration throughout the approach present severe engineering challenges. None of these external deceleration approaches have been demonstrated at any scale relevant to interstellar missions. They remain paper concepts whose practical implementation involves engineering problems that are at least as challenging as the propulsion problems on the outbound leg. The deceleration problem is not a footnote to the energy barrier. It is the energy barrier encountered a second time, with the additional complication that it must be solved at the destination, in a stellar environment that has never been visited, using systems that must have functioned perfectly throughout a decades-long journey through the most hostile environment accessible to any human-made object. Even if the deceleration problem is solved in principle, arrival introduces a second category of difficulties that are often overlooked. A spacecraft approaching another star system at 10% of light speed is not arriving at a destination in the ordinary sense. It is entering an environment about which only limited information is available, after a journey that may have lasted decades, carrying systems that must perform correctly on their first and only attempt. The challenge begins with navigation. A velocity of 10% of light speed corresponds to approximately 30,000 kilometers per second. At that speed, a navigational error that appears negligible at departure can become enormous by the time the spacecraft reaches its target. A deviation of a few millionths of a degree in trajectory can translate into millions of kilometers of positional error after traveling several light years. Course corrections are possible, but every correction requires energy, reaction mass, or some alternative propulsion capability that must itself be carried throughout the mission. The target system is also not stationary. Stars move through the galaxy with their own velocities. Planets orbit those stars, and smaller bodies occupy trajectories that may not be fully known from Earth-based observations. A mission launched toward an exoplanet decades earlier must account not only for where the target is at launch, but where it will be upon arrival. The calculation requires extraordinary precision over timescales far longer than any spacecraft mission in human history. The environment itself presents hazards. At relativistic velocities, even microscopic particles become dangerous. A grain of dust impacting a spacecraft at a significant fraction of light speed carries kinetic energy comparable to an explosive projectile. Throughout the journey, shielding systems must survive continual exposure to interstellar gas, dust, and cosmic radiation. By the time the spacecraft arrives, its protective structures may have endured decades of cumulative damage. The braking system, whether a mag sail, photon sail, or another technology, must still function despite this prolonged exposure. Communication creates another layer of difficulty. The nearest star system is more than 4 light-years away. Any message sent from an arriving spacecraft requires years to reach Earth. Any reply requires years more. The mission therefore cannot depend on real-time instructions. Every navigation decision, every contingency response, every scientific priority must either be determined autonomously or encoded decades in advance. An unexpected problem encountered during arrival cannot be discussed with mission control in any practical sense. By the time a message describing the problem reaches Earth, the spacecraft will already have completed or failed its approach. This autonomy requirement becomes even more demanding if the goal extends beyond a simple flyby. Entering orbit around a planet, deploying landers, or conducting detailed exploration requires a sequence of operations more complex than anything ever attempted beyond the solar system. Every step depends on systems that have remained functional across an interstellar journey, measured not in months or years, but in generations. The result is that deceleration is not merely the final phase of an interstellar mission. It is the gateway to an entirely new set of engineering challenges. Reaching another star is difficult. Arriving there with a spacecraft capable of doing meaningful science may be even harder. The energy required to cross interstellar space is only the first barrier. The precision, reliability, and autonomy required to survive arrival form a second barrier that is no less formidable: the interstellar medium as an active threat. The space between stars is not empty. The interstellar medium is a diffuse mixture of gas, primarily atomic and molecular hydrogen and helium, and dust, consisting of silicate and carbonaceous grains, typically measuring tenths of micrometers in size. In the local interstellar medium surrounding the solar system, the average density is approximately 1 atom per cubic centimetre, a vacuum vastly better than anything achievable in a terrestrial laboratory, where even ultra-high vacuum systems contain billions of molecules per cubic centimetre. At the scale of everyday distances, this density is negligible. A spacecraft moving at escape velocity from Earth's gravity, roughly 11 kilometers per second, encounters so few interstellar medium particles that their cumulative effect over any human timescale is unmeasurable. But kinetic energy scales with the square of velocity. A particle of mass emit speed v carries kinetic energy 1/2 mv squared. At 10% of the speed of light, 30,000 kilometers per second, even a single hydrogen atom carries kinetic energy of approximately 750 electron volts in the reference frame of the approaching spacecraft. That is more than enough to ionize the atom and initiate a chain of secondary reactions in any surface it strikes. For a spacecraft traveling at 10% of light speed, the interstellar medium is effectively a beam of energetic particles, continuously bombarding the spacecraft's leading face. The flux of hydrogen atoms encountered per unit timescales with the spacecraft's velocity and the interstellar density. At 10% of light speed through the local interstellar medium, a spacecraft's forward-facing surface area of 1 square metre encounters roughly 3 million hydrogen atoms per second, each carrying hundreds of electron volts. The cumulative ion bombardment produces sputtering of surface materials, progressive erosion of any unshielded leading face, generation of X-ray fluorescence from stopping radiation, and deposition of kinetic energy as heat. The dust is more severe. Interstellar dust grains in the local interstellar medium have a size distribution ranging from nanometers to approximately 1 micrometer. A grain of mass approximately 1 nanogram. Extremely small by any everyday standard, travelling at the relative speed of 30,000 kilometers per second, carries kinetic energy of approximately 450 joules. That is roughly the energy of a .44 Magnum pistol round, delivered by an invisible dust grain that cannot be detected in advance or deflected. A spacecraft travelling at 10% of light speed through the local interstellar medium would encounter dust grain impacts delivering handgun round equivalent energies at a rate that over decades of travel would progressively crater and erode any unshielded surface. At 20% of light speed, the kinetic energy of each impacting particle quadruples, because kinetic energy scales with velocity squared. Dust impacts at 20% of light speed deliver energy equivalent to rifle rounds. At 50% of light speed, impacts of even sub-microgram particles carry energies comparable to small explosive charges. The breakthrough Starshot analysis team estimated that at 20% of light speed, the leading face of the proposed gram-scale spacecraft would need to be designed to withstand cumulative impacts amounting to the equivalent of kilograms of TNT per square metre over the journey's duration. No material currently known has the combination of low density, high hardness and high tensile strength required to withstand decades of this bombardment, while adding acceptable mass to a spacecraft optimised for minimum weight. The erosion problem worsens with speed and with mission duration, creating a direct trade-off between faster travel, which shortens mission duration but increases impact energy, and slower travel, which reduces impact energy but extends the bombardment period. At every speed in the range considered, the cumulative effect of interstellar medium interaction on any spacecraft carrying passengers or sensitive instruments is severe. Proposed shielding approaches include a thin sacrificial forward shield that absorbs impacts and is progressively eroded over the mission, designed with enough thickness to survive the journey. A liquid metal shield that flows and self-heals after impacts. A magnetic field that deflects charged particles, which would address ions but not neutral atoms or solid particles. A dynamic shield that uses directed energy to vaporize approaching dust grains before impact, which would require continuous power consumption and tracking capability beyond current technology. Each of these adds mass, complexity and power requirements to an already extraordinarily constrained system. The interstellar medium is not a passive environment that an interstellar spacecraft passes through safely. It is an active erosive agent whose effects compound over the decades-long journeys that interstellar travel requires at physically plausible speeds. Accounting for shielding mass, shielding erosion rates, and the additional power required to maintain active protective systems increases the mass and energy requirements of any realistic interstellar mission beyond the already formidable figures based on propulsion alone. Cosmic radiation and the biological limit. Any mission carrying biological passengers, which would be required for any form of crewed interstellar travel, faces a radiation environment qualitatively different from anything experienced in Earth's protected biosphere or even in low Earth orbit. The interstellar medium is permeated by cosmic rays, highly energetic charged particles, primarily protons, with a spectrum extending from tens of millions of electron volts to over 10 to the 20 electron volts, the latter exceeding by many orders of magnitude the energies achievable in the most powerful particle accelerators on Earth. Galactic cosmic rays originate from a variety of astrophysical sources, including supernova remnants, pulsar wind nebulae, and active galactic nuclei. They travel throughout the galaxy, filling the interstellar medium with a roughly isotropic flux. Within the solar system, Earth's magnetic field and the heliosphere provide significant protection. The geomagnetic field deflects lower energy cosmic rays before they reach the atmosphere. The atmosphere itself provides roughly 1,000 grams per square centimetre of shielding equivalent, absorbing or stopping the large majority of cosmic rays before they reach the ground. Astronauts in low Earth orbit within the geomagnetic field receive cosmic ray doses approximately 150 to 200 times higher than ground level. Astronauts beyond the geomagnetic field in deep space receive higher doses still. A spacecraft travelling through interstellar space over decades receives cosmic ray doses substantially exceeding anything studied in the context of current space medicine. NASA's analysis of radiation risks for a crewed Mars mission, a journey of 6 to 9 months in deep space, already identifies cancer risk and central nervous system effects as serious concerns requiring either advanced shielding or acceptable risk tolerance. The cancer risk for a single Mars mission would likely exceed acceptable occupational radiation exposure limits under current NASA guidelines by factors of 2 to 3 without additional shielding. An interstellar mission lasting 40 to 80 years at 10% of light speed exposes crew members to cosmic ray doses hundreds of times higher than a Mars mission. The long-term biological effects of such exposures are not studied in human subjects, and extrapolation from animal data suggests severe consequences, including substantially elevated cancer rates, accelerated neurological aging, cognitive impairment, and increased risk of acute radiation syndrome during periods of elevated cosmic ray flux associated with solar particle events or nearby astrophysical transients. The standard engineering response to radiation hazards in space is passive shielding, adding material mass between the crew and the radiation source. But cosmic rays at galactic energies are highly penetrating. Dense materials like lead are effective against lower energy ionizing radiation, but interact with high energy cosmic rays to produce secondary particle cascades, where a single high energy primary particle creates a shower of secondary particles, some of which are more biologically damaging than the original. Water and hydrogen-rich materials are more effective per unit mass at reducing the secondary cascade problem. But even optimized shielding configurations would need to mass hundreds of metric tons per crew member to reduce cosmic ray doses to acceptable levels. This mass must be accelerated to cruise speed and decelerated at the destination, multiplying the already enormous energy and propellant requirements. The alternative to shielding is accepting higher radiation doses, which requires either biological countermeasures that do not currently exist, or crew selection based on unusual radiation tolerance, or mission duration limits that may be incompatible with the travel times involved. Or it requires accepting that a crewed interstellar mission operates outside the boundary conditions of any currently accepted ethics of human research and exploration. There is no solution to the cosmic radiation problem that does not either dramatically increase the mission's mass and energy requirements or impose severe biological costs on the crew. The physics of cosmic ray penetration and biological damage is not a problem that clever engineering can dissolve. It is the consequence of high-energy particle physics applied to radiation biology, and the remedies are fundamentally limited by the same mass-energy trade-offs that constrain every other aspect of interstellar mission design. The radiation problem becomes even more severe as spacecraft velocity increases. Cosmic rays are not the only source of energetic particles in interstellar space. The interstellar medium itself, sparse as it is, contains hydrogen atoms, dust grains, and heavier elements distributed throughout the galaxy. At ordinary spacecraft speeds, these particles are negligible. At relativistic speeds, they become a form of radiation in their own right. From the perspective of a spacecraft traveling at a significant fraction of the speed of light, every atom in the interstellar medium is encountered with enormous kinetic energy. A particle that would be harmless at conventional velocities can strike the spacecraft with enough energy to damage materials, erode surfaces, and contribute to the radiation environment experienced by the crew. The faster the spacecraft travels, the more severe this effect becomes. The vacuum between the stars is not truly empty, and velocity transforms its sparse contents into a persistent hazard. This creates a paradox at the heart of interstellar travel. Increasing speed reduces travel time, limiting the years the crew spends exposed to cosmic radiation. But increasing speed also increases the energy of collisions with interstellar particles, raising the severity of the radiation environment encountered during the journey. Slower missions suffer from prolonged exposure. Faster missions suffer from more energetic exposure. The optimum balance remains uncertain because no human mission has ever operated under anything remotely resembling interstellar conditions. The problem extends beyond biology. Electronics are vulnerable to radiation as well. High-energy particles can corrupt memory, damage sensors, degrade solar cells, and alter the behavior of computer systems. Modern spacecraft already employ extensive radiation hardening techniques for missions within the solar system. An interstellar vehicle would require these protections for decades without maintenance, replacement, or resupply. Every critical system would need to survive an environment that continuously attacks both living tissue and machinery. Taken together, these effects reveal that interstellar space is not simply a larger version of the space between planets. It is a distinct physical environment governed by different constraints. The distance between the stars is only one obstacle. The radiation filling that distance is another. And unlike many engineering problems, it cannot be completely eliminated. It can only be managed at considerable cost in mass, complexity, and risk. Time, civilizational continuity, and the mission duration problem. The travel times for even the most optimistic interstellar mission concepts raise a category of problem that has no precedent in any human historical or institutional experience: the mission duration problem. Any mission that requires decades to complete involves the deaths of launch personnel, the retirement and replacement of supporting institutions, the evolution of technology beyond the mission's design parameters, and the potential transformation of the society that launched it beyond recognition. Any mission requiring centuries or millennia to complete extends these challenges to encompass multiple generations of institutional succession, cultural transformation, and technological revolution. Humanity's longest duration organized projects offer some calibration for what institutional continuity across time actually looks like. The construction of Gothic cathedrals in medieval Europe sometimes spanned 200 years or more, requiring continuity of craft knowledge, funding sources, and organizational structures across multiple human generations. Even with the powerful institutional backing of the Church and the material record of ongoing construction, many cathedral projects experienced interruptions, restarts, and alterations reflecting the changing priorities and resources of successive organizational periods. The resulting structures often departed significantly from original plans. The Roman Catholic Church, one of the oldest continuously operating institutions in Western history, has existed for approximately 2,000 years. Its continuity across this period involved profound transformations in doctrine, governance, geographic center, cultural character, and institutional relationships. The institution of 2025 differs from the institution of 25 CE in ways that its founders would not recognize and would likely not endorse. Continuity of institutional identity is not the same as continuity of purpose, priorities, or character. A crude interstellar mission to the nearest interesting candidate requiring 400 years of travel time would span a period equivalent to the entire history of the modern nation-state system in Europe. The institutions that launch such a mission would need to remain committed to supporting it, receiving its communications, and preparing to receive its crew through the entire sweep of time from 1625 to 2025. The transformations that occurred in that period, the scientific revolution, the industrial revolution, 2 world wars, the development of nuclear weapons, the invention of computing and the internet, the restructuring of virtually every major geopolitical relationship, represent the kind of change that no institutional commitment of any organization has survived intact. The generationship concept proposed as a solution to the biological lifespan problem for long-duration missions explicitly acknowledges that the mission duration exceeds individual human lifespans and envisions a self-sustaining population that travels, reproduces, and eventually delivers a crew that was born in transit and never knew Earth. The social, ethical, and engineering requirements of such a concept have received serious academic analysis. The minimum viable population to avoid genetic bottleneck effects over many generations is estimated at several hundred to several thousand individuals, requiring a habitat large enough to support a functional human community with maintained social structures, governance, cultural production, education, and psychological health. No human community has ever been maintained in a closed, isolated environment for more than a few years with any degree of stability, and every such attempt has revealed severe psychological stresses from crowding, monotony, interpersonal conflict, and the absence of the environmental variety and stimulation that human psychology appears to require. Extrapolating from months-long isolation studies to multi-century generation ships requires assumptions about human adaptability and institutional design that have no empirical foundation. The generation ship also confronts an ethical problem with no clean resolution. It requires the deliberate creation of human beings who did not choose and cannot escape their circumstances. Children born on a generation ship mid-voyage are passengers in a project they did not consent to, travelling to a destination they did not choose, under conditions they cannot leave. Whether this is ethically distinguishable from other circumstances in which individuals are born into situations they did not choose is a serious philosophical question, but the magnitude of the imposition in a generation ship context, spanning the entire life of the individual in a physically constrained and purpose-determined context, is qualitatively more severe than most ordinary circumstances of inherited situation. There is also no guarantee that a generation ship would remain committed to its original mission. A spacecraft travelling for centuries is not merely a vehicle, it is a society. Societies develop their own cultures, institutions, political conflicts, religious beliefs, and historical narratives. The descendants of the original crew would inherit the mission, but inheritance is not the same as agreement. History provides numerous examples of communities fundamentally redefining their goals over time. Nations change political systems, religions split into competing branches. Colonies seek independence from their founding states. Even organizations created for a specific purpose frequently evolve into institutions pursuing objectives their founders never imagined. A generation ship isolated from Earth for centuries would be subject to the same forces of cultural drift and institutional transformation. The destination itself may eventually lose significance. For the first generation, the target star system is a concrete objective chosen by people who personally participated in the launch. For the 20th generation, it may be little more than a historical tradition. The individuals living aboard would experience the spacecraft, not the destination, as their home. Earth would be a distant historical memory. The target star would be an abstraction. The social and political concerns of daily life aboard the vessel could easily become more important than the mission's original purpose. This raises a practical question that engineering alone cannot answer. What happens if a future generation decides not to continue? A generation ship cannot be piloted by the dead. Every stage of the mission depends on the cooperation of people who were never consulted when the project began. The long-term success of the voyage therefore requires not merely functioning technology, but the continued willingness of successive generations to maintain, support, and identify with a goal established centuries earlier. Even if that commitment survives, the mission confronts another possibility: irrelevance. Technological progress on Earth may continue while the spacecraft is in transit. A vessel launched using the best technology available in one century could be overtaken by a faster mission launched centuries later. This possibility, sometimes called the waiting paradox, creates an uncomfortable question. If future technology can dramatically reduce travel times, does it make sense to launch a slower mission now? The result is that the challenge of interstellar travel is not only physical, it is civilizational. The spacecraft must survive, but so must the culture that gives the mission meaning. The propulsion system must function, but so must institutions, educational systems, governance structures, and social cohesion across spans of time longer than most civilizations have endured. The journey between the stars is measured not only in distance and energy, but in generations, and generations are far less predictable than physics. What the Fermi paradox actually implies. The Fermi paradox is conventionally presented as a mystery. Given the apparent abundance of potentially habitable worlds, In a galaxy billions of years old, where is the evidence of other technological civilizations? The absence of detected signals, the absence of alien artifacts in the solar system, the absence of any clearly non-natural phenomenon that requires intelligent agency for explanation, all contrast sharply with naive estimates of the number of civilizations that should exist if life and intelligence are common occurrences. The standard response to the paradox is to identify a great filter, some point in the development from chemistry to interstellar civilization at which almost all lineages fail. If the filter lies in the past, behind us in evolutionary history, perhaps the development of eukaryotic cells, or sexual reproduction or complex nervous systems, then intelligent life is genuinely rare, and we may be among the earliest in the galaxy. If the filter lies ahead of us, something that almost all technological civilizations encounter and do not survive, the implications are significantly darker. The speed of light offers a different kind of resolution to the Fermi paradox, one that does not require any filter and does not depend on claims about the frequency of intelligent life. The resolution is purely geometric and physical. The galaxy is large enough that even if it is filled with intelligent civilizations, the time required for physical travel between them at physically realistic speeds exceeds the persistence of any civilization, the biological lifespans of any crew, and in many cases, the remaining habitable period of any star system. Civilizations may be abundant and yet permanently isolated from one another, not because they destroyed themselves and not because they chose isolation, but because the physics of space, time, and velocity make contact impossible within any relevant time frame. This resolution is sometimes called the rare communication hypothesis, distinguished from the rare Earth hypothesis in that it does not require life or intelligence to be uncommon. Life may be everywhere. Intelligence may be relatively common. Technological civilizations may have arisen millions of times in the galaxy's history, and yet each one is surrounded by a sphere of possible communication and physical reach that grows at the speed of light outward, but shrinks rapidly in practice when the energy and time costs of actual travel are accounted for. The effective radius of contact for any civilization, defined as the distance from which a reply to any signal can be received within the civilization's active technological lifespan, is measured in tens to hundreds of light years at most. For physical contact, the effective radius is dramatically smaller. Consider the numbers directly. If a technological civilization has a mean active lifespan of 1,000 years, a figure suggested by some analyses of the stability of complex social systems, then the maximum distance from which a communication can be sent and a reply received within that lifespan is 500 light years. The sphere of radius 500 light years centered on Earth contains approximately 130,000 star systems and perhaps a few million individual stars. If 1 in a million of those systems hosted a technological civilization simultaneously present, which would imply tens of billions of civilizations in the galaxy as a whole, there would be expected to be approximately 0 simultaneous technological civilizations within 500 light-years of Earth during any given 1,000-year period. The constraints tighten further for physical contact. A civilization attempting to send a spacecraft to a system 100 light-years away at 10% of light speed commits to a 1,000-year mission. Whether the home civilization remains technologically functional throughout that period, whether the destination civilization remains detectable at the other end, whether any useful exchange occurs, even if contact is made, all become deeply uncertain. The effective range of physical contact, under realistic assumptions about mission duration, civilizational persistence, and propulsion constraints, may be measured in tens of light years, not thousands. The Fermi paradox in this reading is not a paradox at all. It is the expected observation of a civilization confined by the speed of light to its local stellar neighborhood, in a galaxy where the density of simultaneously active civilizations is low enough that none happen to be within the physically accessible range. The silence of the cosmos does not necessarily imply the absence of minds. It may simply imply that the universe is too large and light is too slow for civilizations to find each other before they are gone. This possibility becomes even more plausible when the age of the galaxy is considered. The Milky Way is more than 10 billion years old. Human technological civilization, depending on how it is defined, has existed for at most a few centuries. The period during which Earth has been producing detectable radio emissions occupies a fraction of galactic history so small that it is effectively invisible on cosmic timescales. If other civilizations follow similar trajectories, emerging, developing technology, and eventually disappearing or transforming into less detectable forms, the overlap between any two civilizations may be extraordinarily brief. The consequence is that distance is only part of the problem. Time is equally important. Two civilizations may exist in the same galaxy and never know of each other because they do not exist at the same moment. One may rise and fall millions of years before the other emerges. Their signals may pass through the same regions of space separated by geological epochs. From the perspective of either civilization, the galaxy appears empty, despite having hosted countless others throughout its history. In this view, the speed of light does not merely limit communication, it fragments the history of intelligence into isolated episodes separated by immense distances and timescales. The Milky Way may not be silent because nobody is speaking. It may be silent because every conversation is spread across centuries, millennia, and light years, preventing participants from ever sharing the same moment. The paradox then dissolves into a consequence of physics. A galaxy can be rich with intelligence and still appear empty to every civilization within it. The speed that separates observation from arrival. There is a distinction at the center of every discussion of interstellar contact that is almost never made explicitly, and its absence produces a systematic confusion about what the Fermi paradox actually asks and what the speed of light actually prevents. The distinction is between three fundamentally different activities: observing a distant civilization, communicating with a distant civilization, and physically reaching a distant civilization. These three activities share the speed of light as their governing parameter, but they differ so dramatically in their practical constraints that treating them as a single category produces deeply misleading conclusions. Observation requires only that light or other electromagnetic radiation travel from the observed object to the observer. A civilization 1,000 light years away can in principle observe Earth as it was 1,000 years ago. The technology required is a sufficiently powerful telescope combined with sufficient signal-to-noise processing capability. No energy expenditure beyond operating the telescope is required. No travel is involved. No physical object crosses the intervening space. Only photons, which propagate at the speed of light and require no propulsion, carry the information. The difficulty of observation scales with distance in a way that is challenging but not prohibitive for advanced technology. The signal weakens with the square of the distance, which is a well-understood engineering problem addressed by larger collecting areas and longer integration times. Communication adds a layer of complexity. Not just receiving light from a distant source, but transmitting a deliberate signal that carries structured information and can be distinguished from background noise by a recipient who knows to look for it. The physical requirements are still modest compared to travel: a powerful transmitter, a directed beam, and a strategy for making the signal recognizable. The constraint is temporal. A message sent to a civilization 1,000 light years away takes 1,000 years to arrive. A reply takes another 1,000. A single exchange requires 2,000 years minimum. This is slow beyond any human planning horizon, but is not physically prohibitive for a sufficiently patient civilization or for automated systems designed to conduct communication on very long timescales. Physical travel is categorically different. It requires accelerating a material object to a significant fraction of light speed, sustaining that object through decades or centuries of hostile interstellar environment, decelerating it at the destination, and either returning data by signal or returning physically. The energy costs are measured in fractions of a national or civilizational energy budget per mission. The travel times are measured in decades for the nearest targets and centuries to millennia for anything further. The engineering challenges compound without any natural limit on their severity. Observation possesses an asymmetry that is easy to overlook but fundamental to understanding the structure of the Fermi paradox. Information is far easier to move through the galaxy than matter. A photon emitted by a transmitter requires energy only at the moment of emission. Once emitted, it propagates freely through interstellar space without additional fuel, maintenance, or propulsion. A spacecraft carrying even a small scientific payload must continuously satisfy every requirement imposed by mass: acceleration, structural integrity, shielding, navigation, thermal management, and eventual deceleration. The difference between sending information and sending matter is not a difference of degree. It is a difference of physical category. This asymmetry suggests that any technologically advanced civilization seeking to explore the galaxy would likely rely on information transfer long before attempting large-scale transportation of biological organisms. The first evidence of extraterrestrial intelligence, if it is ever found, is therefore much more likely to arrive as an electromagnetic signal than as a spacecraft. Radio waves, laser pulses, and other forms of directed communication exploit the fact that information can cross interstellar distances at the maximum speed permitted by physics, while requiring only a tiny fraction of the energy needed to transport physical objects. Even observation without communication may be surprisingly effective. A civilization possessing telescopes substantially larger than those currently available to humanity could potentially identify atmospheric biosignatures on distant planets, detect industrial pollutants, observe artificial illumination on planetary night sides, or identify other indirect indicators of technological activity. None of these observations require travel. They require only sufficient collecting area, detector sensitivity, and patience. This creates a situation in which civilizations may know about one another without ever meeting. A sufficiently advanced society could compile extensive astronomical records of inhabited worlds scattered throughout a region of the galaxy, while having no practical means of visiting them. The relationship would resemble astronomy more than exploration. Other civilizations would appear as distant objects of study, observed through light that left them years, centuries, or millennia earlier. The consequence is that the galaxy may not be empty or silent in the way the Fermi paradox is often imagined. Instead, it may be populated by civilizations that remain observationally connected, yet physically isolated. They may detect one another, model one another, and perhaps even exchange occasional messages across enormous spans of time, while remaining forever separated by the same relativistic limits that govern every other process in the universe. The speed of light permits awareness. It does not necessarily permit contact. The confusion between these three categories leads to a common error in reasoning about the Fermi paradox, treating the absence of detected signals as equivalent to the absence of physical visitors. They are not equivalent. A civilization might be broadcasting signals we have not yet detected, or we have not yet pointed a suitable receiver in the right direction at the right time. A civilization might have sent a physical probe that has not yet reached us, or has reached us but is too small to detect. A civilization might be observable in principle by our telescopes without having any practical capability for physical interstellar travel. Mixing these categories produces a confused picture in which the silence of the radio spectrum is taken as evidence that we are alone, or conversely, in which the assumed abundance of life elsewhere is taken as evidence that contact should be possible. Neither inference follows cleanly. The speed of light constrains all three activities, but its constraints on physical travel are so much more severe than its constraints on observation or communication that they constitute a qualitatively different kind of barrier. A civilization that masters observation and communication across hundreds of light years has achieved something remarkable. A civilization that masters physical interstellar travel across the same distances has achieved something that may be fundamentally impossible, given the known laws of physics and the known energy available from any plausible stellar-scale source. Recent developments in exoplanet science and what they change. The field of exoplanet science has advanced with extraordinary speed since the first confirmed detection of a planet orbiting a main sequence star in 1995. The current catalogue of confirmed exoplanets exceeds 5,700 as of early 2026, with thousands of additional candidates awaiting confirmation from the TESS mission and archival Kepler data. The James Webb Space Telescope, operational since mid-2022, has begun characterizing the atmospheres of transiting exoplanets with sensitivity and spectral resolution far exceeding previous instruments, opening a new era of comparative atmospheric science. These developments are scientifically transformative. They establish that planets are ubiquitous throughout the galaxy, that rocky planets in the habitable zones of their host stars are common, and that the chemical preconditions for life, organic molecules, liquid water, and energy gradients appear in planetary atmospheres and surfaces across a wide range of stellar environments. The statistical inference from Kepler data suggesting that perhaps 1 in 5 Sun-like stars hosts an Earth-sized planet in the habitable zone has been broadly confirmed and refined by subsequent analyses, with some studies suggesting the fraction may be higher. But the scientific excitement surrounding these discoveries exists in a specific and important context. Everything known about exoplanets is known through remote observation. The light years of distance between Earth and every known exoplanet system remains intact, unaffected by the sophistication of our observations. Detecting carbon dioxide, water vapor, or methane in the atmosphere of a planet orbiting a star 40 light-years away does not bring that planet closer. It does not reduce the energy required to send a spacecraft there. It does not shorten the travel time. It does not eliminate the deceleration problem, the interstellar medium hazard, or the biological radiation exposure. It means only that we can now observe those distant worlds in considerably more detail than before. This distinction between observation and exploration has appeared repeatedly throughout the history of astronomy. Every major advance in observational capability has expanded humanity's knowledge of distant objects far more rapidly than its ability to physically reach them. The invention of the telescope allowed Galileo to observe the moons of Jupiter in 1610, yet more than 3 centuries passed before a spacecraft visited the Jovian system. Neptune was discovered in 1846 through mathematical analysis of Uranus's orbit, but humanity did not obtain close-up images of the planet until Voyager 2 arrived in 1989. The interval between discovery and direct exploration grows larger as distance increases. Exoplanets represent the most extreme version of this pattern. Unlike the planets of our own solar system, they are separated from Earth not by months or years of travel, but by decades, centuries, or longer. Improvements in telescope technology therefore produce a widening asymmetry. Every generation of instruments dramatically improves what we can know, while leaving almost unchanged what we can physically reach. This asymmetry is especially apparent in atmospheric spectroscopy. When a planet passes in front of its host star, a tiny fraction of the starlight filters through the planet's atmosphere before reaching Earth. Different molecules absorb different wavelengths of light, imprinting characteristic spectral signatures on the transmitted radiation. By analysing those signatures, astronomers can infer atmospheric composition without ever approaching the planet. Carbon dioxide, water vapour, methane, sulfur compounds, and a variety of other molecules can be identified remotely through this technique. The remarkable aspect of the method is not merely that it works, but that it extracts information from systems separated by distances that no human-made object has ever crossed. The photons carrying that information may have travelled for decades before reaching Earth's detectors. Entire planetary atmospheres can be analysed through particles of light that left their source before many of the scientists conducting the observations began their careers. Future observatories are expected to extend these capabilities significantly. Proposed missions such as the Habitable Worlds Observatory are designed specifically to image Earth-sized planets around nearby Sun-like stars and search for atmospheric biosignatures with greater sensitivity than JWST can achieve. If successful, these observatories may produce the first robust evidence of extraterrestrial biology within the coming decades. Yet even a definitive biosignature detection would emphasize the central limitation rather than remove it. Suppose astronomers identify a planet 40 light-years away with atmospheric oxygen, methane, seasonal chemical cycles, and other indicators strongly suggestive of a living biosphere. The scientific importance would be unparalleled. It would demonstrate that life emerged independently at least twice in the universe. Entire fields of biology, astronomy, chemistry, and philosophy would be transformed overnight. But the practical situation would remain unchanged. Any message sent to that world would require 40 years to arrive. Any reply would require another 40 years to return. A spacecraft travelling at 10% of light speed would still require approximately 4 centuries to complete a round trip. The discovery would provide knowledge, not access. Humanity would know that another living world exists, perhaps in extraordinary detail, while remaining separated from it by the same relativistic distances that existed before the discovery was made. In that sense, exoplanet science may ultimately reveal a universe rich with life, while simultaneously demonstrating how difficult it is for life to bridge the distances between the stars. The TRAPPIST-1 system illustrates this precisely. The 7-planet announcement in 2017 was followed by years of JWST follow-up observations targeting atmospheric characterization. Initial results reported in 2023 found no evidence of a substantial carbon dioxide atmosphere on TRAPPIST-1b, and subsequent observations of TRAPPIST-1c also found no strong atmospheric signals consistent with a thick greenhouse atmosphere. These null results do not rule out habitable conditions on the inner habitable zone planets, TRAPPIST-1 E, F, and G. But they illustrate that even with JWST's capabilities, characterizing the potentially habitable worlds in the system requires sustained observational investment over many years. What JWST can detect is the presence of biosignatures in an exoplanet atmosphere. Gases like oxygen, ozone, methane, nitrous oxide, whose simultaneous presence in a planetary atmosphere would be difficult to explain without biological processes. Detection of such a biosignature would be perhaps the most significant scientific discovery in history. It would establish that life exists beyond Earth, and it would change nothing about the physical distance to that life, nothing about the energy cost of sending any physical object there, and nothing about the time required for any physical contact. The practical implication is that exoplanet science, as it advances toward biosignature detection and increasingly detailed atmospheric characterization, will in all likelihood confirm that life exists elsewhere in the universe long before any physical contact with that life is possible. We may establish with confidence that living worlds exist within 50 or 100 light-years of Earth while remaining entirely unable to visit them, send physical emissaries to them, or establish any communication faster than the decades-long round-trip delay imposed by the speed of light. The gap between knowing and reaching will widen as our observational capabilities improve, because the physics governing travel times does not improve with our telescopes. How expansion of space affects the situation. The speed of light as a constraint on interstellar travel operates within the framework of special and general relativity, and a complete account of the physical barriers to contact must address what these theories actually say rather than the simplified version presented in introductory physics. One aspect of this that is rarely discussed in the context of interstellar travel is the expansion of space itself, which affects the most distant objects in the universe but has negligible consequences for galactic-scale distances. Space is expanding. Edwin Hubble's 1929 observation that distant galaxies are receding from us at velocities proportional to their distance established the observational basis for what is now understood as the expansion of the universe driven by what is conventionally called dark energy. The Hubble constant, approximately 70 kilometers per second per megaparsec in current measurements, describes the rate at which space is expanding. A galaxy 1 megaparsec away, approximately 3.26 million light-years, is receding at approximately 70 kilometers per second due to the expansion of space. A galaxy 10 megaparsecs away recedes at approximately 700 kilometers per second. A galaxy 1000 megaparsecs away recedes at approximately 70,000 kilometers per second, well above the speed of light in terms of recession velocity. This recession velocity does not violate the speed of light as a constraint on information or matter transport. It is not the galaxy moving through space at above light speed. It is space itself expanding, carrying the galaxy along with it. The distinction matters physically. Recession due to spatial expansion does not prevent light from traveling between expanding regions, though it does redshift the light and, for sufficiently distant sources, can place them in regions where the expansion is fast enough that light emitted today will never reach us. Within the Milky Way galaxy, the expansion of space is entirely negligible. Gravity within the galaxy binds stars and star systems together against the cosmological expansion. The distance from Earth to Proxima Centauri is not increasing due to the Hubble expansion. The distance to the Andromeda galaxy is actually decreasing, as the Milky Way and Andromeda are gravitationally bound and moving toward a merger in approximately 4.5 billion years. The expansion of space is relevant to extragalactic distances and to the very long-term future structure of the universe, but for the purposes of travel within the Milky Way, it contributes nothing to the barriers that constrain interstellar missions. What general relativity does contribute to the analysis of interstellar travel is time dilation. A spacecraft moving at a significant fraction of the speed of light experiences time passing more slowly than an observer at rest relative to the starting point. At 90% of the speed of light, the time dilation factor is approximately 2.3. For every year the spacecraft crew experiences approximately 2.3 years pass on Earth. At 99%, the factor is approximately 7.1. At 99.9%, approximately 22.4. This relativistic time dilation is often invoked as a potential solution to the biological lifespan problem for interstellar travel. If a crew could somehow reach 99% of the speed of light, they could travel to a star 100 light-years away while aging only about 14 years, experiencing the entire journey within a single working career. The galaxy's 100,000 light-year extent could in principle be crossed for the crew members in roughly 14,000 years of shipboard time at this speed, compared to 100,000 years of external time. The relevance of this to the Fermi paradox and to any practical mission planning depends on what it actually costs to achieve these speeds. At 99% of the speed of light, the relativistic kinetic energy of a spacecraft is approximately 6.1 times its rest mass energy. Expressed through Einstein's famous equivalence, this means the kinetic energy corresponds to 6.1 times the mass of the spacecraft in pure energy equivalent. A spacecraft massing 1 million kilograms would carry kinetic energy equivalent to the complete annihilation of 6.1 million kilograms of matter. Providing that energy through matter-antimatter annihilation, the most energy-dense fuel conceivable within known physics, would require 3.05 million kilograms of antimatter on the outbound leg alone, and the same again for deceleration. The total energy budget for a 1 million kilogram spacecraft decelerating at both ends, for a mission at 99% of the speed of light to a star 100 light-years away, exceeds 10 to the 25th joules. That is approximately 100,000 times the total annual energy production of current human civilization for a single mission. And antimatter production is so energy inefficient that providing this fuel would require vastly more energy input than the annihilation energy produced, multiplying the true energy cost by factors that make the number physically absurd. Time dilation is real physics. Its consequences are confirmed by experiments with atomic clocks on aircraft, by precision measurements of particle lifetimes in accelerators, and by the operation of GPS satellites, which must correct for relativistic effects to maintain positional accuracy. But exploiting time dilation for practical interstellar travel requires operating at relativistic speeds that impose energy requirements no physically conceivable civilization can meet through any known mechanism. It is a real effect attached to an impossible condition: the rare communication hypothesis and its implications. The resolution to the Fermi paradox, most consistent with the physical analysis developed in this script, is not the rare Earth hypothesis, which claims that life or intelligence is uncommon, and not the self-destruction hypothesis, which claims that civilizations reliably destroy themselves before achieving interstellar capability. It is what can be called the rare communication hypothesis. Life and intelligence may be common in the galaxy, but the physical barriers to interstellar contact are so severe that civilizations never make meaningful contact with one another, regardless of their abundance. This hypothesis has several distinct components that must each be evaluated. First, that civilizations are limited in their physical reach by the speed of light and the energy costs of propulsion. Second, that the timescales for even the most modest physical missions exceed the persistence of most civilizations or the biological lifespans of most crew members. Third, that the galaxy's spatial distribution of civilizations and the temporal distribution of their active periods combine to make simultaneous presence within physical contact range vanishingly unlikely for any given pair. And fourth, that even electromagnetic communication is so time delayed across meaningful galactic distances that it fails to constitute contact in any practically meaningful sense. The first component has been developed in detail through the preceding chapters. The speed of light is the ceiling, and realistic propulsion concepts operate far below it. The energy costs at any significant fraction of light speed are measured in fractions of planetary or stellar energy outputs per mission. The travel times to all but the nearest stellar neighbors extend across multiple human generations or civilizational persistence periods. The second component depends on what is meant by civilizational persistence. Human civilization, in its current technologically sophisticated form, has existed for roughly a century in anything that would be recognizable as a global, interacting, scientifically capable civilization. We have no reliable basis for estimating how long such a civilization typically persists. The fossil record tells us that complex multicellular life has existed on Earth for approximately 540 million years. The hominid lineage extends approximately 2.5 million years. Homo sapiens with modern anatomy has existed for approximately 300,000 years, and with modern behavioral complexity for approximately 50,000 to 100,000 years. Writing and recorded history spans approximately 5,500 years. The Industrial Revolution, which produced the technological capability for global communication and eventually space travel, is roughly 250 years old. Each step in this sequence is enormously shorter than the preceding one. Extrapolating from this single data point to a typical civilizational lifespan is epistemologically treacherous. But the reference distribution from Earth suggests that the period during which any civilization would be both willing and capable to pursue interstellar missions might be measured in centuries to millennia. Against the travel times of thousands to millions of years for missions across galactic distances, this creates an enormous mismatch. A civilization must remain capable and motivated to support or receive a mission for longer than it is likely to persist. The third component, the spatial and temporal distribution problem, can be illustrated quantitatively. If 1,000 civilizations were active simultaneously in the Milky Way today, the average distance between them would be roughly 300 to 400 light-years. For any given civilization, the nearest neighbour would be, on average, perhaps 100 to 200 light-years away. A one-way signal to that nearest neighbour takes 100 to 200 years. A round-trip communication exchange takes 200 to 400 years. Physical travel at 10% of light speed takes 1,000 to 2,000 years. Both the receiving civilization and the sending civilization would need to persist in recognizable and interested forms throughout this period for any exchange to be meaningful. If 1 million civilizations were active simultaneously, the average separation drops to roughly 100 light-years, improving the numbers somewhat. If 10 billion civilizations were active simultaneously, approaching an implausibly high density of 1 per average star system, the average separation would be a few light-years, and communication and travel timescales would drop to tens of years and decades respectively. But 10 billion simultaneously active civilizations would require essentially every moderately sized star to host one, a density orders of magnitude beyond the most optimistic estimates, consistent with the apparent silence of the cosmos. The temporal distribution compounds the spatial problem. 1,000 civilizations existing over the galaxy's 13 billion-year history need not exist simultaneously. If each persists for an average of 10,000 years and they are distributed randomly through galactic history, at any given moment, only a small fraction would be simultaneously active. The probability that any two civilizations whose physical separation would allow contact within their respective active periods are simultaneously present in the galaxy at the right time is very small. The rare communication hypothesis, therefore, does not require civilizations to be uncommon. It requires only that the physics of contact, governed by the speed of light, is severe enough that contact rarely occurs even among many civilizations. The number of civilizations required for the hypothesis to be false, for contact to be expected and observed by at least some civilizations, depends on the assumed typical active period, the achievable travel and communication speed, and the required threshold for meaningful contact. Under realistic assumptions about these parameters, the Fermi paradox resolves not as a mystery, but as the expected observation. What remains when the shortcuts fail? The analysis of interstellar travel is incomplete without addressing the proposed shortcuts that are frequently invoked in popular discussions as potential circumventions of the speed of light constraint. Wormholes, warp drives, higher dimensional travel, and quantum entanglement communication are the most commonly cited. Each deserves honest examination: what the physics actually says, what would be required to exploit the concept in practice, and why the claimed circumvention either does not work as advertised or requires conditions that are physically impossible under known or plausible physics. Wormholes are solutions to Einstein's field equations of general relativity that describe geometrically connected regions of space-time that need not be spatially adjacent in the ordinary sense. A traversable wormhole would allow a traveller to enter at one mouth and emerge from a different, spatially distant mouth after traversing the wormhole's interior. If the wormhole mouths are separated by a large spatial distance, the traveller could cover that distance in far less time than it would take light travelling through ordinary space, effectively achieving faster than light travel in the sense of covering a spatial distance in less time than light requires. The Reissner-Nordstrom and Kerr solutions for charged and rotating black holes contain mathematical structures resembling wormholes, but theoretical analysis shows these are not traversable in practice. They collapse faster than any physical signal can traverse them. and any perturbation of the geometry closes them. The Morris-Thorne traversable wormhole solution, published in 1988, demonstrated that traversable wormholes are allowed by general relativity, but only if they are threaded with exotic matter, a material with negative energy density. Ordinary matter has positive energy density. Negative energy density is a concept from quantum field theory, where the Casimir effect and certain quantum states can produce regions where the local energy density is lower than that of the vacuum, technically negative relative to the vacuum baseline. These quantum vacuum effects are real, but produce energy densities many orders of magnitude too small and too localized to thread a macroscopic wormhole. The energy scale required to create or maintain a traversable wormhole of size sufficient for a spacecraft to pass through is estimated to be of order the total mass energy of a planet or a star, in the form of exotic matter. No mechanism is known to produce exotic matter in such quantities. No theoretical framework developed subsequent to the Morris-Thorne paper has reduced this energy requirement to physically plausible scales. As of 2026, traversable wormholes remain a mathematical curiosity of general relativity with no experimental support, no proposed physical production mechanism, and no pathway from concept to engineering. The Alcubierre warp drive, proposed in 1994, describes a space-time geometry in which a region of space contracts ahead of a spacecraft and expands behind it, creating a bubble that carries the spacecraft along at superluminal velocities without the spacecraft itself exceeding light speed locally. This is mathematically consistent with general relativity and does not obviously violate causality in the original formulation. But the original Alcubierre metric requires exotic matter with negative energy density in quantities corresponding to roughly minus the mass energy of Jupiter, and the negative energy required is not of the small Casimir type, but of an entirely different scale, with no known physical origin. Harold White's 2011 proposed modification of the Alcubierre metric altered the geometry to reduce the exotic matter requirement, but subsequent analysis by Fenning and Ford and others showed that all traversable warp drive metrics require exotic matter with negative energy, and that no manipulation of the geometry can eliminate this requirement. A 2021 paper by Eric Lentz proposed a warp drive solution using only conventional positive energy, generating substantial media coverage. Subsequent analysis by theoretical physicists identified that Lentz's solution required energy densities comparable to the mass of Jupiter concentrated in the warp bubble's walls, and that the energy conditions it satisfied were not the relevant ones for practical traversable warp drive operation. As of 2026, no warp drive proposal has demonstrated practical viability, and the consensus among physicists working in the field is that traversable warp drives require physics beyond the Standard Model and general relativity as currently understood. Quantum entanglement is frequently cited in popular discussions as a potential faster-than-light communication mechanism. Quantum entanglement is a real phenomenon, confirmed by countless experiments in which the quantum states of two particles are correlated in ways that cannot be explained by classical local hidden variable theories, as demonstrated by Bell test experiments. When a measurement is made on one entangled particle, the result is instantaneously correlated with the state of the other particle, regardless of the distance between them. This correlation does not allow faster-than-light communication. The no communication theorem in quantum mechanics proves rigorously that no manipulation of one entangled particle can be used to transmit information to the location of the other entangled particle faster than light. The measurement result at each location is statistically random, and the correlations between the two random results can only be discovered by comparing the measurement records through a classical channel, which is constrained to light speed or below. Quantum entanglement is a genuine non-local correlation, but it cannot be used to send information, because neither party can control or predict their measurement outcomes, only compare them after the fact through ordinary communication. Quantum teleportation, a related concept, uses entanglement to transfer the quantum state of a particle from one location to another. This process also requires a classical communication channel to complete the transfer, and the total time for the teleportation is limited by the time for the classical channel to operate. No information and no material object travels faster than light in any teleportation protocol. The name is misleading. Quantum teleportation does not move objects through space. It transfers quantum state information, and it does so no faster than the speed of light. When all the proposed shortcuts are examined honestly, none of them provide a physically demonstrated or theoretically plausible circumvention of the speed of light constraint under known or near-future physics. This does not mean that future physics will not reveal unexpected possibilities. The history of physics contains genuine surprises, from quantum mechanics to dark energy, that were not anticipated by earlier frameworks. It is possible that a future theory of quantum gravity or some other currently unanticipated development could reveal a mechanism for traversing space faster than light. But responsible reasoning about the Fermi paradox and about the prospects for interstellar travel cannot be founded on the hope for unknown future physics. It must be grounded in what we know, which says clearly that no shortcut currently exists or is theoretically plausible at any accessible energy scale. What alien technology could plausibly achieve? The argument that sufficiently advanced alien technology could overcome the barriers described in this script deserves direct engagement rather than dismissal. It is a serious argument that is sometimes used to suggest that the Fermi paradox implies something more mysterious than the simple physics of travel time and energy cost. The response to this argument requires careful distinction between barriers of engineering and barriers of physics. An engineering barrier is an obstacle that arises from limitations of available technology or materials. Building a bridge across a river is an engineering barrier. Given enough material and design sophistication, any river can be bridged. An engineering barrier can in principle be overcome by a civilization sufficiently more advanced than current humanity. A civilization 1 million years older than humanity would have had vastly more time to develop technology, accumulate knowledge, and solve engineering problems that appear intractable to us. A physical barrier is an obstacle that arises from the laws of physics themselves, independent of technology or materials. The second law of thermodynamics, which prohibits perpetual motion machines, is a physical barrier. The uncertainty principle, which limits simultaneous knowledge of position and momentum, is a physical barrier. The speed of light as a ceiling on velocity is a physical barrier. These barriers cannot be overcome by more advanced technology because they are not imposed by the limitations of technology. They are imposed by the structure of nature. The barriers to interstellar travel at speeds approaching the speed of light are partly engineering barriers and partly physical barriers. The inability to achieve exhaust velocities approaching light speed with any known propulsion concept is partly an engineering barrier. With sufficiently advanced materials and energy sources, higher exhaust velocities might be achievable. The energy cost of kinetic energy at relativistic speeds is a physical barrier. The kinetic energy of a mass moving at a given fraction of the speed of light is fixed by the laws of relativity, and no technology can reduce it. The deceleration requirement is a physical barrier. Momentum must be conserved, and changing a spacecraft's momentum at arrival requires the same impulse as changing it at departure. The impossibility of exceeding the speed of light is a physical barrier grounded in special relativity and confirmed by every precision test of that theory. An alien civilization far more advanced than humanity could plausibly achieve better propulsion than we currently possess. Fusion propulsion, antimatter propulsion, laser sail systems at scales far exceeding current conception all represent engineering achievements that a mature technological civilization might accomplish. These improvements could reduce travel times to nearby stars, from thousands of years to centuries or decades. They could reduce the energy cost per mission from civilizationally prohibitive to merely enormous. They represent genuine progress against engineering barriers. The distinction becomes clearer when compared to other areas of technological progress. Human civilization has repeatedly transformed what once appeared impossible into routine engineering achievements. Crossing oceans required months under sail and substantial risk. Today, it requires hours. Communication across continents once depended on physical messengers. Today, information moves globally in fractions of a second. These advances can create the impression that all limitations eventually yield to technological innovation. History encourages technological optimism because so many previous barriers proved to be engineering problems rather than physical ones. Interstellar travel is unusual because the underlying constraints remain unchanged regardless of technological sophistication. Better engineering can improve efficiency, reliability, and scale. It can reduce waste and exploit energy sources currently beyond our reach. What it cannot do is alter the relationship between mass, energy, momentum, distance, and time, established by fundamental physics. A spacecraft built by a civilization 1 million years more advanced than ours would still inhabit the same relativistic universe. The equations governing its motion would be the same equations that govern ours. The details of implementation might change dramatically. The limits themselves would not. They cannot reduce the travel time to the nearest star below approximately 4 years, because the nearest star is 4.24 light-years away, and nothing can travel faster than light. They cannot reduce the deceleration energy below the kinetic energy of the arriving spacecraft, because conservation of momentum is absolute. They cannot make a journey of 40 light-years take less than 40 years, regardless of the sophistication of the propulsion system, unless some form of faster-than-light travel is achieved, which requires physics beyond what is currently understood or evidenced. The specific question for the Fermi paradox is whether alien technology advanced enough could make interstellar contact routine rather than rare. Routine contact would require travel time short enough relative to civilizational lifespans to be practical, energy costs low enough relative to available resources to be affordable, and interstellar distances short enough relative to achievable speeds to be bridgeable within relevant timescales. Meeting these conditions requires either much higher speeds than physics currently permits or much shorter distances than the galaxy actually presents. Neither is achievable through engineering advancement alone. An alien civilization might develop a technology we cannot currently imagine. But any technology that truly circumvents the speed of light requires either new physics or new mathematics, not just better engineering. If such physics exists, we have not yet found evidence of it. If it will be discovered in the future, we cannot reason about its properties today. The responsible conclusion from current knowledge is that the barriers to interstellar travel are predominantly physical rather than engineering barriers, and that no foreseeable level of technological advancement can dissolve them. The civilizational calculus of a mission. Even setting aside the physical barriers and accepting for the sake of argument that some civilization somewhere possess propulsion technology sufficient to cross interstellar distances in decades rather than centuries, the decision to undertake such a mission involves a civilizational calculus that has no precedent and that presents obstacles as significant as the physical ones. What does a civilization gain from sending a physical mission to another star system? If the mission is robotic and one-directional, the gain is scientific data from the destination system transmitted back at the speed of light over the years or decades following arrival. The data is valuable, but the same basic information, atmospheric composition, surface conditions, presence of biological activity indicators could be obtained through sufficiently advanced remote observation at far lower cost. As telescope technology advances, the argument for expensive physical missions relative to cheap remote observation weakens progressively. If the mission is crewed and returns, the gain is crew experience from direct presence at the destination, samples brought back, and the demonstration of a capability that has both scientific and cultural value. But the duration of the mission, measured in decades for the nearest targets, means the mission crew departs from one civilization and returns to a different one. The scientific knowledge accumulated during the mission is transmitted back in real time by signal. The crew returning physically adds the samples and the testimony of direct experience. But the primary scientific value is in the signal data, not the physical return. The additional value of returning the crew physically, relative to the cost, is modest. If the mission aims to establish a colony or outpost at the destination, the calculus changes, but the costs increase enormously. A colony requires vastly more mass than a research mission, including genetic diversity sufficient for long-term population viability, agricultural systems, construction materials, medical equipment, and the full infrastructure of a self-sustaining community. The energy costs scale with the mass, and the mass for a viable colony is orders of magnitude greater than for a research probe. The colony must also be capable of surviving in the destination environment without any physical support from the home civilization for the entire duration of any problem that requires physical rather than signal-based assistance. The motivation for a civilization to undertake such a mission depends on what that civilization values and what pressures it faces. A civilization facing existential threat from its home star's evolution might be motivated to establish colonies elsewhere, regardless of cost. A civilization driven by exploration and scientific curiosity might launch probe missions to nearby systems. A civilization seeking to expand its population and resource base might invest in colonial missions. But in each case, the decision must be weighed against alternatives that do not involve crossing light years of space. A civilization facing existential threats from its home star could potentially address those threats by engineering solutions within its own system, migrating to a more distant orbit, constructing orbital habitats, or terraforming other bodies in the system. These options are enormously cheaper in energy terms than interstellar colonization and do not require crossing light years. A civilization seeking scientific knowledge can acquire most of it through remote observation, using energy costs far below those of physical missions. A civilization seeking to expand population has, for any plausible population level short of Dyson sphere occupancy, ample room within its own stellar system. There is also a temporal dimension to the cost-benefit analysis that is easy to underestimate. Most large-scale projects undertaken by human societies produce benefits on timescales relevant to the individuals funding, building, or politically supporting them. Even projects lasting decades generally deliver intermediate results that justify continued investment. An interstellar mission may not. The individuals who authorize it may never see it arrive. The engineers who build it may be dead before the first major scientific return. Entire governments, economic systems, and cultural priorities may change repeatedly before the mission reaches its destination. This creates a problem not of physics, but of motivation. Maintaining commitment to a project whose primary rewards lie generations in the future requires a level of long-term planning rarely demonstrated by complex societies. The challenge is amplified if the same resources could produce immediate benefits closer to home. Every civilization, regardless of technological sophistication, must allocate finite resources among competing priorities. A mission whose rewards arrive centuries later must compete against projects whose rewards arrive next year. For this reason, the rarity of interstellar travel may reflect not only physical difficulty, but economic and social incentives. A civilization capable of reaching the stars may simply find that there are very few circumstances in which doing so is the most rational use of its resources. The civilizational calculus therefore suggests that interstellar missions are, even for a technologically capable civilization, a marginal use of resources compared to alternatives that achieve similar goals at lower cost. This does not mean no civilization would ever undertake such a mission. But it suggests that the frequency of interstellar missions, even among technologically advanced civilizations, might be much lower than naive assumptions suggest, contributing further to the rarity of physical contact between civilizations. The prison that lets you look. The cruelest feature of the universe's structure, from the perspective of any civilization that has developed enough intelligence to contemplate the cosmos, is that the same speed of light that makes interstellar travel essentially impossible also enables comprehensive observation of the universe's contents. The speed of light is simultaneously the mechanism by which we can see the galaxy in extraordinary detail, and the mechanism by which we are permanently separated from what we see. A civilization with advanced telescopes can study the atmospheres of exoplanets, detect the biosignatures of living worlds, characterize the stellar populations and galactic structure across hundreds of thousands of light years, observe the births and deaths of stars and galaxies, map the large-scale structure of the universe, and accumulate a scientific understanding of the cosmos that encompasses billions of light years in every direction. All of this is possible because light carries information at 300,000 kilometers per second, enabling electromagnetic observation of the entire observable universe from a single, fixed location. And all of it is observation only. The exoplanet atmospheres detected by JWST are at distances of tens to hundreds of light years. No human instrument, no human-launched spacecraft, no physical object of any kind has ever left the solar system and reached another star system. The most distant human artifact, Voyager 1, is currently approximately 23 billion kilometers from the Sun, or roughly 0.0024 light years. The nearest star is 4.24 light years away. Voyager 1, after nearly 50 years of continuous travel, has covered less than 0.06% of the distance to the nearest star. This gap between the reach of observation and the reach of physical presence is a structural feature of any universe in which the speed of light is the universal ceiling. Any civilization that develops sufficiently powerful telescopes will be able to observe the cosmos in detail, vastly exceeding its ability to physically interact with what it observes. The universe presents its contents as a spectacle visible from any location, while making those contents physically inaccessible to any civilization confined to a single stellar system by the speed of light. The asymmetry between observation and interaction becomes even more striking when considered in terms of information itself. Observation is fundamentally passive. A telescope does not need to alter a distant world in order to learn about it. The photons arriving from a planet's atmosphere, a star's surface, or a distant galaxy are already carrying information produced by natural physical processes. The observer merely collects and analyzes that information. The energy cost is local and comparatively small. A telescope with a larger mirror or a longer observation time can extract increasingly detailed knowledge without requiring any physical influence on the distant object. Interaction operates under entirely different constraints. To physically affect another star system requires transporting matter, energy, or both across interstellar distances. Every kilogram of mass must obey conservation of momentum. Every signal is limited by the speed of light. Every attempt to establish a physical presence must contend with the immense scales separating stars. The result is that the universe permits information to spread far more easily than material influence. This distinction is visible even within our own solar system. Humanity learned the composition of the Sun through spectroscopy long before it could send spacecraft beyond Earth orbit. We measured the atmospheres of the outer planets before any probe reached them. Knowledge consistently expands ahead of physical access because information can travel on photons while explorers must carry mass. On interstellar scales, the difference becomes overwhelming. A civilization may eventually catalogue thousands of inhabited worlds, estimate their climates, identify biological signatures in their atmospheres, and even infer aspects of their ecology, all while remaining permanently unable to visit them. The map grows continuously more detailed, even as the territory remains unreachable. The philosophical consequence of this structure is distinctive. A civilization can become deeply familiar with the properties of worlds it can never visit, life it can never meet, and phenomena it can never directly investigate. It can develop sophisticated models of distant environments, predict conditions on exoplanets with some accuracy, and understand the physical processes governing every class of astrophysical object without being able to send any physical representative to any of them. Knowledge and presence become permanently decoupled. The universe is comprehensible but not reachable. This decoupling has implications for how we should think about the Fermi paradox. A civilization advanced enough to observe biosignatures on exoplanets may be confident that life exists elsewhere without having any practical mechanism for establishing contact. The observation confirms the existence of other living worlds, while the physics of travel confirms the impossibility of reaching them. The Fermi paradox in this reading is not a mystery about why we don't see aliens visiting. It is a consequence of a universe in which seeing and visiting are governed by the same physical constant, but constrained by it in radically different ways. We can see, we cannot go. And any civilization that has developed to our level or beyond has discovered the same thing. The universe extends its entire contents to observation while withdrawing them entirely from physical reach. It is a cosmos that permits knowledge without contact, that displays its living worlds without allowing their occupants to meet, that presents the illusion of accessibility through the very mechanism that enforces permanent isolation. What this means for the search and for us. The physical analysis of interstellar travel and its implications for the Fermi paradox does not make the search for extraterrestrial intelligence pointless. It reframes what the search is and what success would look like. The search for electromagnetic signals from other civilizations, pursued primarily through radio and optical frequencies by organizations including the SETI Institute and the Breakthrough Listen Initiative, targets the one form of interstellar contact that the speed of light makes possible at meaningful distances: communication by light-speed signals. If a civilization exists within a few hundred light years and has been broadcasting detectable signals in our direction for long enough that those signals have reached us, the search could in principle detect them. The constraint is that a round-trip communication exchange would require centuries, meaning any detected signal would be a one-way broadcast rather than a dialogue, and any response we sent would not receive a reply within any currently living person's lifetime. This is a genuine limitation of the search, but it does not make detection meaningless. A detected signal from another civilization would establish with certainty that we are not alone, that intelligence has arisen elsewhere, and that the physical universe supports the development of technological civilizations capable of deliberately broadcasting across light years. This would be among the most significant scientific discoveries in human history, transforming our understanding of life's place in the cosmos even in the absence of any practical two-way communication. The search for techno-signatures, observable consequences of technological activity that can be detected through astronomical observation, extends the search beyond deliberate communication. Atmospheric chemical disequilibrium from industrial processes, megastructures that modify the light curve of their host star, waste heat signatures from large energy processing installations, all represent potential techno-signatures that could be detected at interstellar distances. Current searches are beginning to address some of these possibilities, and near-future telescope capabilities will dramatically expand the sensitivity and coverage of techno-signature searches. What the physical analysis constrains is the expectation that any detected civilization would be capable of visiting us, or that our response to any signal would be received and acted upon within any practically relevant time frame. The constraints are severe, and acknowledging them changes what success in the search means. Success is not finding a civilization that will come to us or that we can reach. Success is knowing they are there, establishing the existence of intelligence beyond Earth, and participating in the one form of exchange the universe permits across interstellar distances, the exchange of light. For us, the civilization that first developed the physical understanding of these constraints and then chose to continue the search anyway, the effort means something beyond its practical implications. It means looking honestly at a universe that is vast beyond intuitive comprehension, that contains billions of potentially habitable worlds across hundreds of billions of star systems, and that simultaneously constrains every mind in every one of those systems to its own small neighborhood by the prison of the speed of light. It means acknowledging the isolation without accepting it as the final word, and choosing to listen anyway across the decades and centuries that signals take to arrive, because knowing that others exist somewhere in the dark is worth the wait, even if the distance can never be crossed. The speed of light is too slow to bring aliens to Earth. It is almost certainly too slow for us ever to reach any civilization that might exist within the galaxy. The distances are too vast, the energy costs too high, the timescales too long relative to any human or civilizational duration. This is not a temporary technological limitation that the next century will overcome. It is the structure of the universe as it actually exists, encoded in the constants of nature that determine how fast anything can travel through space. And yet we are here, looking. A species that evolved on a rocky planet, orbiting an ordinary star in the outer arm of a galaxy containing hundreds of billions of similar stars that developed over a few 100,000 years. The capacity to understand the laws of physics, to build instruments that detect photons from billions of light years away, to calculate the distances to other stars, to understand precisely why those distances cannot be crossed in any human lifetime, and to continue searching anyway. Whatever the universe has produced elsewhere across its billions of light years and billions of years, it has produced this here. A mind that knows the prison and keeps looking for the light through the bars. The invisible wall between civilizations. The speed of light is 299,792,458 meters per second. It is the fastest anything in the universe travels. It takes more than 4 years to cross the distance to the nearest star. It is too slow. Not too slow for physics, which is built around it, not too slow for the everyday experience of a species on a planet 12,742 kilometers wide, but too slow for the galaxy, which measures its distances in units of years of light travel. Too slow to make physical contact between civilizations at any distance beyond the nearest stellar neighbors without energy expenditures that strain or exceed civilizational output, without travel times that exceed civilizational lifespans, without enduring an interstellar environment that degrades any physical structure over the decades of transit required. Too slow, in the most physical sense, to allow the galaxy to know itself through the physical meetings of its inhabitants. The Fermi paradox dissolves when its assumption is corrected, the assumption that abundance implies contact. Life may be everywhere. Intelligence may have arisen across the galaxy many times in its 13 billion-year history. And every mind that has looked up at the stars has faced the same calculation and reached the same conclusion. The distances are measured in light years. The travel times are measured in generations. The energy costs are measured in civilizational outputs. The physics does not offer a shortcut. We are not necessarily alone. We may be surrounded by life at distances that light itself requires years to cross. And we will most likely never meet any of it, not because we have failed to develop the technology, not because they have destroyed themselves, not because the universe is hostile to intelligence, but because the universe is very large. Light is the fastest thing in it, and even at 299,792,458 meters per second, the distances between the fires are greater than any flame can bridge.